Hello, this is Daryl Korn, and I'm going to go over my final project for deep learning algorithms. Let's get into it. Starting with the code for my VGG model for the RGB data. So I start by bringing in all of my packages, and then here I'm setting mixed precision floats. I read in the textbook that this can help increase training time if it's done correctly. In my experience, it did help with that. So that was very nice. Then we bring in the data here from Kaggle. Here we set the batch size. We are allowing our model to be fully trainable here. We do not want it to be partially trainable, and we are not using any data augmentation. Here is where I bring in the files. So I'm using the image dataset from directory method, bringing in the patches data or the RGB patches, and I split the training data into validation data as well. I use 10% of it, and I resize it to 64 by 64. And I'm shuffling the training, but I'm not shuffling the validation or the test data set. And for the test data set, I'm using the provided validation data, which is a little confusing, but that's what happened. So on to bringing in the convolution pre-trained model. We don't include the top, and we set it to 64 by 64. Here's some logic in case I set the base to be partially trainable. And then we are going to be using a very low training rate right here. Or, sorry, learning rate. Low learning rate. Then we define our early stopping. I check my monitoring the validation loss, waiting about 15 epochs before we restore the best weights. And then uh, here's one pre-process step that I have where we rescale it to be normalize the RGB values. Then we define some data augmentation of horizontal flip, random rotation, and random zoom. Here we compile it. We just take the convolution base, flatten it, then two dense layers with some L2 regularization. And then we compile it. We have all of our metrics right here using a categorical cross-entropy loss. Okay. Here we are actually pre-processing our data. So we pre-process the train, validation, and test data sets where, it is rescaling our data and it's augmenting the training data if we prefer. Okay, then we fit our data and we evaluate our model right here. Looks like that. I have to calculate the F1 score manually because I'm using an older TensorFlow version. That's just what I got working with my GPU. And here we got we save the model. We make a rudimentary confusion matrix because I didn't have time to figure out how to do that on my own through sklearn. It works though. And then we display our training and validation, loss and accuracy. We display the validation F1 score as well as the training F1 score. But something went awry in my code, but it's displayed for the infrared model. And lastly, we display the training validation area under the curve. Okay, that's all there is to it. For the infrared model, it's the exact same thing, really, except here I bring in the train thermal patches instead of the train RGB patches. And it's all the same after that. So nothing really to go through there. Except here the F1 model graph is working as intended. Okay, let's analyze some results then, because that's what's really interesting, isn't it? So I'll discuss my experiments a little bit, but in order to save time, and I think it's more important to talk about the results anyway. So I'm not going to go too far into this, but I used three different model structures for my CNN experiments. Two of them one had a really low amount of parameters at 388,000. The other one was close to a million. And then I made a third model structure where I tried to copy the VGG16 structure. So it was like 14 convolution layers, up to 7 dropout layers, regularization, low learning rate, all that good stuff, up to 15 million parameters. And that ended up Well, I'll talk about that later. Um, but in total, all of these experiments, for when you include RGB and thermal data sets, I had 68 experiments with the CNN structure. And here are the results for the RGB data set. What seemed to work best was having a high amount of parameters with data augmentation, and sometimes dropout helped for other ones. And similar for the infrared data set, what seemed to give the best results was a high number of parameters here, along with some regular L1 regularization, which is different from the RGB. Okay, on to the VGG experiments. So for this one, I took the convolution base and I removed the top layers and I put two dense layers on top. Sometimes I try it with a dropout. Sometimes I use regularization. Sometimes I use data augmentation. Um, but the three amounts of parameters that I tested was fully trainable base layer, which led to about 15 million parameters, a partially trainable base layer, which is about 13.5 million parameters, and then a fully untrainable base layer, which only had 500,000 trainable parameters. So all of these tests combined for the RGB and thermal data sets was about 60 different tests. And the results of this are displayed here. What seemed to help the VGG model the most was adding dropout and L1 regularization, sometimes L2 regularization. But similar as before, what really made the difference was just increasing the number of trainable parameters. So that model could, I guess, it had more room to learn the data. So here was my best performing RGB model overall, actually, which I'll talk about more later. Oop, we went too far. Here we go. Um, and the same results really happened for the thermal data set too, for my VGG model. The dropout and regularization really seemed to improve it, as well as just having a ton of trainable parameters, because this was also my best performing thermal model as well. Okay, now let's talk about the autoencoder a little bit before we go into the results. The model structure I tried for this, anywhere from like 4 to 6 convolution layers in the encoder and the decoder. Some dropout, some regularization, some data augmentation, and anywhere from 8.5 to 17.5 million parameters. All of this combined to about a total of 30 tests for the RGB and thermal data sets. So for the RGB data, it seemed that L2 regularization really seemed to help it, as well as, just having a ton of trainable parameters, Um, and for the thermal model, interestingly, the it was happier with less trainable parameters at 8.5 million, but it still liked that L2 regularization. So okay, on to our results. And sorry for the amount of graphs here, but it's a lot of data to include. And you only got 20 pages. So, but what I'll mostly be talking about is these confusion matrices over here, because I think that lets you compare the models in the most succinct way. So, just some patterns that I found for the CNN model. It seemed to confuse a lot of cars and buses. That turned out to be a pretty reoccurring theme throughout the data set, throughout all my tests, because those classes are quite similar. But interestingly, the CNN model, it actually guessed more buses as cars than actual buses. So just a lot of false positives there, which the other models didn't have as much of. Um, Something to say about the VGG16 is it had the best distinction between cars and buses. It actually guessed more buses correctly than as cars, unlike CNN. And for the encoder, I mean, the auto encoder was kind of worse in every way. But something to say for it, it had a really difficult time with the sign class. It had much more false positives in this column here than any of the other models did. So my best model overall for the RGB was the VGG16 at 96.6% accuracy. Okay, and then to just dive into the comparison just a little bit more, and show some actual examples. The CNN was pretty accurate with this multi-person bike, which was unique. The other models, they got this thing wrong, which it does seem to occupy a weird space in uh, with vehicles because it does kind of look like a car, I suppose. And the VGG16, some things I noticed it was doing, the other ones didn't do as much, is that it often confused lights with signs or people. And so this one, it kind of could look like a sign that's just a black square. And I really thought these tall, long ones were people as well. And something interesting about the autoencoder is that it struggled to classify cars with bright taillights at night. So this one, it had a lot of this one was classified as a light because I guess it was just so bright. The autoencoder got confused. And this one, it's also bright that it thought it was a sign. Okay. And now to just dive into why my best model, the VGG 16, may have classified some things incorrectly. So for the bike class, it got a lot of these this four-person bike, these images incorrect, as well as this bike here behind a signpost. So those are pretty tough questions for it, I suppose. As for buses, it thought a lot of these boxier buses, um, it thought that they were cars or trucks. And for cars, it thought boxy looking cars were buses. So I guess it just kind of got confused to the line between those two classes. And this one, it's just a super low resolution image of a car. So I guess it just really picked up on its tail light and it thought it was a light. For lights, I mentioned earlier that these dark boxy ones I thought were signs and these tall ones I thought were people sometimes. As for motorcycles, it kind of confused them with people or bikes, which I get why it might mistake it for a bike. They do look similar. And I suppose that there are always just people in these images, so that's why it may have gotten that wrong. Um, as for people, one thing I noticed here in figure 12 is that a lot of my models got this particular image wrong of the dude in the high res vest. I think there may have been something strange going on, like maybe the whole picture of him standing at the truck may have been in the training data set or something. And then he's just like a subset of that larger image, so it gets it wrong often. But it was interesting to see this uh, be wrong time and time again throughout all of my models. And as for figure 11 here, I mean, I suppose that there are a lot of people included in bike photos because it doesn't really look anything like a bike, so that one's harder to defend. As for signs, same as light. It got this dark sign wrong. It thought it was a light, so I guess they do look similar. I'll give it that. And then this one, I can't really tell what's going on in figure 14. I suppose it makes context in the larger image. It makes more sense in the context of the larger image, um, but there's not a lot of features to go off of there. And as for the truck class, the one on the right, the figure 16, that is a pretty low resolution image, so I can see how I got that wrong. And then from this angle, it does look like a bus in figure 15. So I'll give it that. Okay, time to go through this now. We're at 13 and a half minutes, so I'll try to be quick. Um, some things that I noticed, we're comparing my thermal models now between each other. So for the CNN thermal models, I noticed that it really struggled between the bus and truck classes. Like it only got one correct for the truck and only got a handful correct for the bus. For the VGG, it was the only one to classify a good number of trucks. It got 10, whereas the autoencoder and the CNN both only guessed one. And it also did very well on the person class as opposed to the other two, which they had way more false positives. And the autoencoder, it interestingly labeled a large amount of person images as cars, which the other two did not do that. It's kind of interesting. Okay, now to dive into why they may have gotten these things wrong. So the CNN, it confused a lot of the side profiles of bikes and cars, where the others did not. And I suppose, they kind of do look alike, really, with these grayscale images. For the VGG, one thing I noticed about is that it was actually very good at classifying pretty difficult person images. So both of these images, the autoencoder and the CNN got wrong, but the VGG got right. Lastly, for the autoencoder, it got a large number of buses incorrect, and it said that they were cars, which is interesting because they don't really look a lot like cars. So it was really struggling there. Okay, let's dive into why the VGG got some images incorrect. Um, since the VGG was my best thermal model as well. So for the bike class, I suppose these are images of a bunch of bikes lined up, and I got very confused by that. I got that incorrect. It said that they were people. For the bus class, just like all the other models, it's kind of confusing buses, cars, and trucks. But these are pretty low resolution images, so I can see it is confusing as to what they are. As for the car class, they're confused with buses, and these are some pretty strange looking cars, so I'll give it that, especially figure 6 here. As for the light, it thought a lot of them were signs, which makes sense when the image is in grayscale. They do look like signs. For the motorcycle classes, it confused them for cars, which I suppose from a side profile, they do kind of look like a car from the side. For the person class, once again, we have that interesting um, uh, sorry, my dog. We have a this person, which is classified incorrectly many times over, and some of the other person images, I think if they had a weird silhouette, it would often get that image wrong for the person. As for signs, I can't really tell why it got the signs incorrect. It just did. And for the trucks, once again, they're confused for cars or buses from bad angles or low resolution. Okay, so time to compare our RGB model with our infrared model. And after comparing the two confusion matrices listed here in figure 7 and figure 6, I noticed that the RGB model is better on the car, light, sign, and truck classes. It got a higher percentage of those images correct, whereas the thermal model was better on the bike, bus, motor, and person classes. So I think this indicates that um, color may be a good indicator for some of these classes. For instance, it did way better on the light class, maybe like over 20% more were correct on the RGB model. And similar for truck, it was about 13% more images were correct for the RGB. Whereas for the thermal, um, I suppose it was just better at picking out people, which were probably contained in these other classes, such as like bikes, buses, and motors. Those typically had more, people included in them, and it seemed to pick out people slightly better than the RGB model. Okay, so let's summarize the project. I found that the VGG16 pre-trained model had the best results on both data sets. And I got the best results when I allowed all the base layers to be trainable. I used a very small learning rate, and I put L2 regularization on both of the models. I did not use any data augmentation or dropout layers. And after doing all those steps, I found that the RGB model tended to perform better on the car, light, sign, and truck classes, and the thermal model performed better on bike, bus, motor, and person classes. So that is all I have for the final project. Thank you for listening, and I will meet with the TA soon to predict some images. So thank you.